Woohoo! Factorial repeated ANOVAs. We're going to make this quick. Short and sweet. I don't think the textbook gets into this enough. It just kind of brushes on it at the end. But I think it's important that we cover it and we talk about it and you have some awareness of it. Here would be an example. And I want you to think about how this is similar to and yet different than the other ones we've done. So Dr. Evans wishes to evaluate various coping strategies for pain. He obtains 8 volunteers to come to the lab on 2 consecutive days. On both days, the volunteer plunges their hand into freezing cold water for 90 seconds. The idea here is that we are inducing pain. They rate how painful the experience is on a scale from 1 to 50. After 30 seconds, 60 seconds, 90 seconds. So we have a repeated measures factor here that we're doing 30, 60, and 90 seconds. But we have them on 2 different days. So the first day they do that, and they're giving pain avoidance instructions. And on the other day, they're giving pain concentration, given instructions to concentrate on the pain. So one day they're told to avoid thinking about the pain, another day to focus on the pain. So there's 2 different conditions, and they have 3 different times, 30 seconds, 60 seconds, and 90 seconds. So in order to counterbalance, if he had everyone do the focus on the pain the first day and everyone do the pain avoidance on the second day, they might have some learning effect because they've done this twice. They might have some fatigue that they're just really not into it at this point. They cannot even on the second day. So to counterbalance for that, half of the students, 4 of them, have the avoidance on the first day, and half of them have the concentration on the first day. And then they switch for the second day. Now, there is another thing going on here. He's doing them on 2 different days. Now, the choice to do this on 2 different days has a couple different implications. First, because they're on different days, we have this natural break between them, and that allows for a washout period. There is a complication, a negative side to it, though. You have to be able to get the people to come back. So when you're having a washout period, deciding how long it needs to be is an important consideration because you want it to be long enough that you truly wash out the effect of the first phase, but not so long that you lose people to follow up. There's no perfect time. Sometimes we just go with our best that we can. So in this scenario, what is the repeated measure factor or the repeated measure factors, and what are the levels of each of them, and what is the outcome variable? Let's start with the outcome variable. That's usually a little easier to pick up. The outcome variable is the thing we're trying to monitor. Now here we're monitoring it not once, but we're having them rate their pain multiple times. So the pain rating is our outcome measure. But each person doesn't rate it once. They rate it 3 times on the first day and 3 times on the second day. So we could say they have 6 ratings, but 2 of them are after 30 seconds. 2 of them are at 60 seconds and 2 of them are at 90 seconds. One of them's under pain avoidance. One of them's under pain focus or concentration. So we could do it 6, but usually we do a 3 by 2. We have 3 time points, 30, 60, 90, under 2 different focus versus focus on the pain versus avoid it, 2 different mental conditions. So 2 by 3 gives us the 6 combinations. 6 combinations, but we're making them by 2 by 3. 2 conditions of what they're doing with their mind and 3 time periods, 30, 60, 90 seconds. So the first repeated measure, we could think of 30, 60, 90, that's time. There are 3 levels to time. The other factor is what instructions they were given to do, the avoidance or the concentration. So that would be their strategy, and there are 2 levels to strategy. 2 levels to strategy, 3 levels of time, combined for 6 measurements per person on the pain scale. Outcome is pain scale, repeated measures are factor and strategy. Generally, ordering. It would be important to have half do the strategies in one order and half do the reverse order. Usually, when we're counterbalancing order A and order B is not included in the model. So we just say that the factor has no effect. It's counterbalanced because we have an equal number in order AB as we do in BA. Half of them have avoidance before concentration, the other half have concentration before avoidance. So because it's balanced, we don't put order into the model. Here's another. Dr. Chapman wishes to examine the effects of drug A and drug B, as well as their interaction on blood flow. Each drug has two possible formulation or levels. So we have two forms of each level of each drug. And it doesn't say here, maybe one formulation is a shot and the other formulation is a pill. So we've got drug A and drug B and two formulations. That's a total of 4 combinations, 2 and 2, 4. So it's a two-way. Which drug, which formulation, meaning shot or pill. So we could have shot of A, shot of B, pill of A, pill of B, 2 by 2, because we have drug and formulation are 2 ways. And then we're going to measure over, and they're given the combinations on 4 different days. The half-life of each drug was such that there were no carryover effects. So this, I guess, you give it to, it might be like ibuprofen or Tylenol that only has 6 to 8 hours and then it wears off. So if we give them on different days, we're good. So let's see, we've got order A1, B1, A1, A1, B1, A1, B2, A2, B2, B1, different ordering. Okay, the outcome here is going to be blood flow. I guess we're looking at blood flow over these 4 different combinations. Okay, this is one way that the data can be set up, where we have these, and this is a factorial, sometimes this is called a panel design because we have the different panels. So we have these 3, and then we repeat 3, and then we repeat 3. The thing to note here is that for when we have multiple repeated measures, if we have 2 or more repeated measures, each of the repeated measures gets their own error term, and there is a different error term for the interaction. So the first repeated measure, if that's drug, gets the error term that's drug by subject interaction. The second repeated measure, which is formulation, gets the formulation by subject interaction term. And if we want to look at the interaction between drug and formulation, it would have a third error term. So when we look at the summary table for these ANOVAs, it's going to have 3 parts. It's going to have at least 6 important lines in the full table. We'll have the first repeated measure factor and its error term. The second repeated measure factor, here it's in blue, and its error term. And then third, in green I have it, the interaction between the 2 repeated measures with their interaction with the subject as the error term. I wouldn't get too worried about the mathematical formulas. If you enter these things right into the program, it will calculate them correctly for you. In R, you would put both of those factor names inside the parentheses for being repeated. And you get effect sizes, partial and regular. These are a little bit more complex formulas, but they still are interpreted the same way. And there still can be an omega squared. So the procedures are usually the same for multiple comparisons, whether you're doing a one-way repeated measure or a 2-way factorial repeated measures. In all of these ANOVAs, if you ever have a significant F-test, the F-test is overall, omnibus. It says the levels of this factor are not all the same. But if the factor has more than 2 levels, say 3 or 4, you need a follow-up test to figure out which levels are different. And this is the case for repeated measures, that we need to do these follow-ups to the omnibus F test. So they can be more complicated for the contrast statements. We can do simple or pairwise. That's more, if we're doing simple comparisons or pairwise comparisons, usually we can use the t-test. But sometimes when we're doing the follow-up to repeated measures interactions specifically, we'll follow it up with a one-way ANOVA or a one-way independent groups ANOVA to make the results easier to comprehend and figure out. But by and large, the best way to figure out these non-significant interactions is with the marginal means. Always the marginal means plots. And we often call these an interaction plot. They can help you really understand where things are the same and where the significance differences are. If we have only one of our repeated measures that is significant, then we can look at a one-way repeated measures ANOVA, and we can do t-tests on the marginal means. And we would still have to worry about do we do Fisher's correction, Tukey's correction, a Bonferroni correction? Do we need a Chaffee's correction for complex comparisons? But again, visualizing those means, plotting a means plot, is very crucial to understanding these results. If there is ever an interaction, you should not try to think in terms of the main effect. The idea of an interaction is the effect of A depends on B. And so to look at only A by itself is counterintuitive. And I think that that's something I want to stress over and over and over again with in the statistical foundations class, is when you have an interaction, interpret the interaction. Don't worry about the main effects, because main effects are collapsing across the other factor on which it's dependent. Okay. When you report your results, always we want to summarize our information. And usually in the type of things that we're going to summarize, we're going to need a table, especially when you get multiple factors. If you have two repeated measures or two independent groups or an independent groups and a repeated measure, you're going to want means tables or a plot of the means with standard errors or standard deviations or confidence intervals. You're going to want some visual summary, whether it's a table or a figure, of the raw data. What are the trends that we're seeing in the raw data? After we do our ANOVA and present the F-tests with their effect sizes, yes, you need effect sizes. Now, there are some people, I say you only need an effect size if it's statistically significant, but this slide was initially forever ago built by Jamison Fargo, and he said that you need effect sizes even if it's non-significant result. And the reason that some people believe that, and I'm not going to argue too strongly against that, is that sometimes we have non-significant results because our test is underpowered. That if we had had a bigger sample size, it would have been declared statistically significant. I'll give you that. So I would always err on the side of giving more effect sizes rather than less. So whenever in doubt, give an effect size. And with ANOVA F-test, that's some form of the eta squared. If something's significant, you definitely need to follow it up with a post hoc or a follow-up test, whether that's a t-test, a contrast statement, an interaction contrast, or a reduced one-way ANOVA. And you need to tell which ones you did, all of the ones you did, not just the few you want to cherry pick to put in your results, but you also need to say, did you do multiple comparisons corrections? And if so, which multiple comparison correction? And again, the mean differences, especially for an interaction, should be graphically displayed. So have a means table to begin with and an interaction plot at the end. And not only will this help you in writing up your results, but it will help others in digesting your results. We say a picture's worth 1,000 words. Well, it's only if you do it right. So it's very important to do it right. Okay, there are some problems with ANOVAs, especially repeated measures ANOVA. We can have problems with validity. Now, longitudinal studies are sometimes touted as the best gold standard, and they are when you're trying to look at change over time, but there are problems with longitudinal studies. Things happened over the passage of times that we can not be aware of. I mean, right now with COVID-19, we're going through something that's big. And if we were doing a longitudinal study and trends were like this, especially say we were looking at economic trends, all of a sudden we're going to see, all kinds of wild things. And you can't always predict those. We also have things that just naturally change over time that if we're studying time's effect, it's going to muddy the water. So sometimes we need methodological controls. So comparison groups are always very important. Another problem with repeated measures design is a benefit is we need fewer participants because we are going to leverage the participants we have by measuring them repeatedly. But if we have a smaller sample size, sometimes that can make our generalizability to a larger population questionable, because since we only have a few, it's harder to ensure that a few subjects are representative of the whole population. So that's just something to consider when you are planning a repeated measures design is, what's the time frame? Are we doing this over days, weeks, months, or years? Are there things that can go wrong or can muddy the water besides just plain losing people? And if we're only using 3 or 4 or 5, is it going to be enough subjects to generalize? We want to be even more vigilant in making sure our sample is random and representative when we're doing this, because each person counts for more. If you are going to do matching, you better do it well, because a poorly matched design study is worse than no matching. Another thing, small samples can lead to all sorts of power problems. Violations of assumptions can make it so that our results are crap. So the last bullet here is with missing data. So anytime we have repeated measures, whether that's over time or under different conditions or 3 different surveys meshed into one, we're asking more of the subjects we do have, instead of doing cross-sectional and only putting people in one group. If we're asking them to do all 3 different conditions instead of one condition, we're putting more pressure on the participants we have, and they're more likely to, their mice die. People just decide it's not worth their time. And when we have dropout with ANOVA methods, it's a big problem. And the reason is we have to have complete data. If we have 4 time points and someone only has 3 of them, we can't use them at all. If we have 3 conditions and someone does the first, gets dizzy during the second one, and can't do the last one, can't use them at all. And that's a big shortcoming of ANOVA methods, is we have to have complete data. And if we have missing data, we got to throw the person all the way out. And there are some methods like multiple imputations for missing data and full information maximum likelihood FIML methods. But by and large, it's a problem with missing data and ANOVA. There's the last slide. Really, we're done with chapter 15. This last slide is a repeated measures by subject ICC calculation. ICC can be used for inter-rater reliability, a measure of correlation. It has lots of other uses. I just wanted to throw that out there on the slide. It's not covered in the chapter, but you can calculate ICCs with these repeated measures factors. And the main use I see it as an inter-rater reliability measure, but it's a little bit more complex than that, and we don't want to get all the way into it. So we'll call 16 or 15 done.